the RSNA, this is the Radiology Artificial Intelligence Podcast. My name is Paul Gee, and I'm a radiologist at the University of Maryland and co-host of the podcast.
And my name is Tenjani, and I'm a radiology resident at the University of Texas Southwestern Medical Center and co-host of the podcast. Each month, we dive into the hottest topics in radiology AI and talk with leading experts, thought leaders, and movers and shakers in the field.
Welcome to this episode of the Radiology AI Podcast. Today, we catch up with Jacopo Teneggi and Dr. Jeremias Sulam to talk about Jacopo's recent RSNA Research Prize for his project titled Weakly-Supervised Learning Substantially Reduces the Number of Labels Required for Intracranial Hemorrhage Detection on CT. Jacopo Teneggi is a PhD student at the Johns Hopkins University Department of Computer Science. He is a recipient for the RSNA 2022 Trainee Research Prize in Imaging Informatics. His research interests include formal interpretability for deep learning models, the theoretical foundations of weakly supervised learning, and its applications to medical imaging and general computer vision tasks. Dr. Jeremias Sulam is an assistant professor in the Department of Biomedical Engineering and is also affiliated with the Mathematical Institute for Data Science and Center for Imaging Science. Dr. Sulam's research focuses on machine learning, sparse recovery, and inverse problems in general and biomedical imaging tasks. His research also involves devising methods for the safe and responsible use of machine learning tools.
Welcome, everyone, to another episode of the Radiology Artificial Intelligence Podcast. Since our last episodes where we discussed building an AI lab from the perspective of a radiologist, as well as the AI fireside chat at the RSNA, we've had a chance to reflect on a lot of the exciting developments as well as challenges and opportunities in building multidisciplinary teams. And on today's episode, we're really excited to have two good friends and colleagues of mine from Johns Hopkins University, Mr. Jacopo Teneggi of the Computer Science Department, and Dr. Jeremias Sulam of Biomedical Engineering. Welcome to the show, Jacopo and Jeremias.
Thank you. It's great to be here.
Thank you so much for the invitation, guys.
It's our pleasure. Thanks so much. So before we begin, just to give a primer, the reason we've invited both of you on the podcast is because you provide really interesting perspectives of a lot of things that we've talked about on the podcast. Things like how do we build a multidisciplinary research group in AI? How do we tackle things like data curation and technology development from the computer science world and the biomedical engineering world into radiology? And so I want to ask, just as an introduction, tell us a little bit about yourselves, how you got into artificial intelligence, and then specifically into medical imaging.
So on my side, I did my PhD in computer science at the Technion in Israel. And back then I was working mostly on signal and image processing problems, but also trying to understand what are good models for natural data, and then how we can harness those models to better process data more efficiently, to solve harder problems, and to basically make inference about measurements. Now, because of the tools that we were handling, we sort of realized that a lot of those tools were very useful also to analyze modern complex machine learning predictors. And so because of that, I became increasingly interested in machine learning and eventually in deep learning problems. But then again, my original training in my bachelor's was in biomedical engineering. And so my heart has always been close to biomedical engineering problems. And so even while studying these settings and these theoretical challenges, I've always find it very fulfilling and satisfying to go back to understanding how these problems impact specific applied problems in biomedical engineering and in biomedical imaging in particular. And in 2018, I was lucky enough to come to Johns Hopkins, where is in some sense a perfect playground at the intersection of the research in methods and computer science, but also applied to a variety of problems in the biomedical sciences.
Thanks so much, Jeremias. And how about you, Jacopo?
Okay, so I'm a PhD student. So I just joined, I'm a first year PhD student at Johns Hopkins in the computer science department. I'm a student of Jeremias. We've been working together throughout my master's, which I took at Johns Hopkins in biomedical engineering. And for my bachelor too, I'm a biomedical engineering by training, but I wanted to wonder in more of the theoretical weeds and challenges that we face with current modern machine learning, especially applied to medical imaging. That's sort of always been there. I cannot recognize a moment where I was like, that's what I want to do. Also, we will see if that's gonna keep staying what I do. But yeah, very excited to be working in this very exciting and challenging environment here at Hopkins for sure.
And I think one of the fruits of this collaboration was your recent project that we saw at RSNA. And it's actually one of the reasons we wanted to talk to you more on the podcast here. So congratulations on your RSNA Trainee Research Prize for Imaging Informatics for the project titled Weakly-Supervised Learning Substantially Reduces the Number of Labels Required for Intracranial Hemorrhage Detection on Head CT. So tell us about the inspiration for this project and tell us more about what you found and how you think this is impacting the field.
Thank you so much. So with talking with Jeremias and Paul, and we were wondering whether these expensive image level annotations that are usually collected by recruiting expert radiologists, for example, the RSNA, intracranial hemorrhage data sets, or these big, huge efforts that require volunteers of expert radiologists to commit thousands of annotation hours. So we were wondering whether these labels actually provided any significant performance advantage compared to training these models, for example, for intracranial hemorrhage detection with just examination level labels. So just to give an example, instead of telling me whether this image contains hemorrhage and this one doesn't, and this one does, and this one doesn't, and then using this annotations to train a machine learning model, what if we just used examination level labels? That is, what if you just told me that this entire scan containing maybe 20, 30, 40, 60 images contains hemorrhage somewhere? Does current modern machine learning models, do they suffer from this changing labeling strategy, or does it not really matter? Because if it doesn't, then maybe this means that we should rethink about how we recruit expert radiologists to collect these data sets in the first place. And maybe this process shouldn't be so tedious and time consuming on their end.
That's very exciting. Jared, Paul, anything to add or any thoughts there?
I would perhaps just add the remark that, it's in machine learning and particularly in supervised learning, we are used to training. The de facto way of training these models is by collecting a whole bunch of data with labels. And depending on what setting you're in, there's an associated cost to what it means to collect these labels. In radiology in particular, these labels come associated with a very high cost, both in time and expertise and monetary costs as well. And it's important to understand how much of this is needed, because obviously these become bottlenecks in the development of large data sets, which in turn lead to practical tools. And so the question is, what is really the trade-off that we should be thinking about when we collect these data sets? How much do we really have to rely on expert annotations that are very precise and very detailed versus annotations that are perhaps coarser and more general, easier to collect, but less precise? Can we still take advantage of that information in order to alleviate a lot of the costs associated to collecting data, in particular in radiology?
And I can add from the clinical side, when we approached this problem, Jeremias and Jacopo asked me if there might be a use case where some of these emerging techniques could have some use. And the first thing that came to mind was the RSNA Intracranial Hemorrhage Challenge. This has been well documented, published in our journal about the data set curation process. This was a Herculean effort of like dozens of neuroradiologists spending hundreds, if not thousands of hours to annotate hundreds of thousands of images for the presence or absence of bleeds. And the implication of this work was really that you could take just examination labels, like Jacopo said, perhaps through natural language processing of radiology reports, maybe flagging exams that are flagged for critical findings, And just on the basis of those very cheaply obtained and scalable kinds of labels, achieve similar performance to models trained with those painstakingly annotated image level labels. But what I thought was really interesting, I'm curious what Jeremias and Jacopo think about this, is at least in one of the external data sets, the performance, the external validity actually was better for the model trained in a weakly supervised fashion on the examination level labels as opposed to the strongly trained model. And, I think one thing that we're always talking about, certainly within the journal and in the radiology community, is, an algorithm. It does well on an internal test set. How does it do well on an external test set? So I thought that to me was one of the most interesting findings, that it actually not only performed similarly, but in one case, it actually did better than the strong label model.
Yes. So just to clarify, Paul, for everybody who's joining this conversation, so when you are referring to multiple instance learning, you're referring to this approach of learning from labels that have less information, that are more general, as in labeling an entire scan, as opposed to
Yes.
strongly supervised learning, where we have access to labels per image slice within the scan. And like you were saying, we observed some small but important differences in how both of these models generalize to external datasets. And it is definitely interesting. The concepts that these models are learning differ, and we understand that. We don't understand exactly how they differ, but at least empirically, we see that the one that is obtained through this multiple instance learning approach that requires less labeling does generalize better in the cases that we studied.
So I've got a question. What do you guys think is the next step? Can we start applying this to like pretty much every type of volumetric type of imaging study? There's a lot of RSNA challenges that have happened since the intracranial hemorrhage challenge that will happen. So I wonder, how scalable do you think this is, or applicable to other types of imaging tasks?
This is just a first dent. And what you're talking about sounds very, very exciting to me. And I would love to see more work on, developing all the tricks of the trade that we are sort of comfortable with at this point with supervised learning, but that we do not necessarily know for weakly supervised learning. As we mentioned in our work, the scope of our paper for now is simply on convolutional neural networks. It would be super exciting to see this applied to more modern and maybe interesting architectures such as vision transformers and all these new models that are coming out every day, and keep beating the state of the art and see if these trends translate, or how far they translate, or how strong these trends are, and where the trade-offs fall if you change domain, if you change model. Maybe it's not just the data, it's also something else. And it would be super exciting to figure that out.
Yes, so just to complement what Jacopo said, it is certainly true that basically we decided to focus on the problem of hemorrhage detection in HET CT. But the overarching question is still general, right? What are general trade-offs of providing labeled data in order to learn classification models? And that question is still open. Empirically, we've shown very encouraging results in this problem of brain hemorrhage detection in brain CT. Probably other, I wouldn't be surprised if other conclusions held in other tasks in radiology as well. But more broadly, I think the question of how to understand the amount of information that is contained in labels and how to best devise guidelines to annotate data sets, generally speaking, is still very much open and of very clearly important practical relevance.
And so say that this approach generalizes and becomes the standard of how we label our data before training models. Are there implications in terms of the level of domain expertise needed to start labeling examinations? And related to that, do you start seeing less disagreement and addressing issues of label multiplicity, where now you have to have education between multiple different labels? Is this work headed in that direction, or is that a totally separate area to tackle?
That is a fascinating question. So this is certainly related. And for the following reason, these labels being more general, you're correct that in some sense they require less a degree of expertise. And in fact, we know for a fact this is true in other settings. For example, the same fundamental ideas and the same fundamental sort of model architectures that Jacopo has been employing in this work, another student in my group, Shengsheng Wan, has used for the task of tumor segmentation in digital pathology. And there we've shown that indeed one can provide these coarser labels by deploying, let's say, a lesser degrees of expertise, either by inexperienced annotators or in a time constrained setting where one cannot dedicate the same amount of focus to the job, and still do very well in detecting the concepts, in this case, tumor. So these questions, the questions that you posed, is certainly related. It is hard to say exactly to what extent or how this will impact the level of expertise that we would need from our clinical partners. Obviously, it is not true that we will be able to dispense of that clinical knowledge. Just as an example, this clinical knowledge, and in particular Paul's collaboration, was crucial for us to get to work to this problem and to solve this task and really understand all the factors at play. But beyond that, at the bare minimum, these concepts still need to be validated from a clinical expertise point of view. So I think that these ideas are moving in the direction of perhaps better understand and better complement the level of expertise that we have from our clinical collaborators.
Jacopo, what about you?
I mean, we talk about this every day for hours in front of the whiteboard, so I would say we're pretty much aligned on these thoughts. Yeah.
So one thing that really bore out to me in this study was just the importance of collaboration, at least from my perspective as a radiologist. These techniques were very novel to me. They were very exciting. And so, I think that this project couldn't have happened, certainly not in my wheelhouse. But I'm wondering, Jeremias and Jacopo, what your approach is. I know, Jacopo, your primary appointment is in computer science, but Jeremias, you're in BME. I'm curious what your perspectives are, just from the engineering side. Do you see the importance also in a similar light of working with physicians and engineers across the table?
I think so. I've thought about this because it was great to be at the RSNA for the first time. It was the first time I was at a meeting such as it's huge. It's something that you need to see to believe it. And talking with Jeremias as well, yes, definitely, because it feels from the engineering side, it's still difficult sometimes to grasp how much the problems that we get all excited about and we think are useful are actually going to have an effect on your pipeline, on your life and the patient's life, which is ultimately what we're all interested in. So yes, definitely collaboration is key here to understand. Yes, we know these mathematical tools, what the things that we can solve, but it's mostly about the story that you tell with these things and how you actually have an effect on the patient's life in after diagnosis, before diagnosis, and all of these things. So yes, definitely very excited to bridge the gap between what we do and what is actually useful, and also understand what we're missing sometimes to actually bridge these claims to real clinical settings, because that's also a very important aspect that sometimes engineers, us, we just sweep under the rug sometimes.
Thanks for joining us for this episode. We hope you enjoyed the conversation. Check out the second part of this conversation in the next episode of the Radiology AI Podcast. Thanks to all of our panelists for their expert insight on this topic.
We hope that you've enjoyed this episode of the Radiology Artificial Intelligence Podcast. Shout out to Uriah Shemchisen for our podcast music and to the RSNA podcast staff.
Email us at podcast@rsna.org anytime with questions, feedback, or suggestions.